Okay, now we're moving on to numbers in base 16. Now, last lecture we saw how base 10 was the natural base for humans because we have 10 fingers. Most of us do have 10 fingers. Base 16 appears in human society quite a lot too. This is because of the unique properties of the number 16. Let's have a look at some of those properties of the number 16. Number 16 is an exact square of a 4. So 4 squared or 2 to the power of 4, both 16s. Some other unique points of the number 16. The first 4 odd numbers, 1, 3, 5, 7, add them up, they make up 16. A compass rose divides up equally into 16 points. Chessboards have 16 black and 16 white pieces. They are divided into 4 quadrants of 16 squares each. Some more facts about 16. Bookbinders use a standard format, something known as 16mo, where the paper gets divided up into 16 leaves or 16 pages. Caterpillars usually have 16 legs, only 6 when they become butterflies. Pre-decimal imperial weights and measures used 16 ounces to a pound. Programming in base 16. We don't actually program in base 16. Computers can only store and manipulate data using binary. They can only store ones and zeros due to the fact that computers use power, electricity, to charge transistors or charge capacitors. Very early computers were programmed and using binary by highly trained mathematicians. They were, of course, prone to a lot of errors. If you can see this kind of represents some of the ones and zeros or bits which would be switched on and off as the computers were being programmed. Look at this image here. What do you see? We see fish with scales, but we see lots of them. And the more you look at these, the more we humans get confused. And as you are getting confused with fish, in the same manner, if there were lots of numbers written in binary, if you had very large numbers written in binary, it's very, very easy to get confused. So we have to find a way of using or representing these very large binary numbers in something that's a bit easier for humans to work with. And that method, folks, is hexadecimal. We have to find that conversion. Base 2 doesn't convert to base 10 very easily, as we saw. However, base 16, base 2 to 16, is pretty straightforward. Now, remember when we looked at base 2 and base 10, we said base 10 has 10 symbols, base 2 has 2 symbols, therefore base 16 must have 16 symbols. And the symbols that are used in base 16, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and A, and B, and C, and D, and E, and F. There are our 16 symbols. After 9, A represents 10, B is 11, C is 12, D is 13, E is 14, and F is 15. That's the 16 symbols. Those are the numbers that we have at our disposal. This is the table that we use with base 16. 16 to the power of 0, any number to the power of 0 is just 1, so that's 1, 16, 256, 4096 and 65536. Remember these 5 column numbers in base 10. These are the most important numbers which are going to allow us to convert from base 16 to base 10 and base 10 to base 16. So we need to memorize these numbers. So a hexadecimal number then, made up using those symbols which we have at our disposal. We're using these symbols. We again align those in accordance with the column which we are working with. So if we had a hex number 18A09, then this would be represented in base 10 as 1 times 65536 plus 8 times 4096 plus A, which is 10, 10 times 256 plus 0 times 16 plus 9 times 1. You write that out as a big sum, add them all up, and we end up with the equivalent base 10 number. So 1 times, 8 times, 10 times, 0 times, and 1 times. And that's the hex multiplying the column base 10 value. Here are some examples of hexadecimal numbers as they are displayed or used in the operating system. There's some here. This is showing the memory range of some sorts with an old device called a modem. Old device. So this would be the same equivalent for modern day devices, of course. When you have some kind of fault, it's showing some hex here. And again, that's the equivalent. If you converted that, it's a long binary number. So instead of showing us a very long or large binary number, we are displaying this as a hex number. Color is represented using hex. There's this color here then that we are seeing. This color here, that bit here, is F4, F5, C5. If that was represented in binary, it'd be a long list of ones and zeros, not very easy to work with. And here's some more hex numbers. So hex has been created only for humans, because we humans, supposedly inferior to computers, that's a controversial topic, isn't it? Well, we can't really make sense of very long binary digits, especially when we're shown a whole bunch of these. So the hexadecimal base 16 makes sense because it's straightforward to represent those large binary numbers here. You may be asked to convert numbers in base 2 to hex. Let me show you how we can convert long binary numbers to hexadecimal and how easy it is to do this. So here's a large binary number. The first step we do is use our concept of a nibble, which is 4 bytes. We divide this binary number up into groups of 4. You see what happened? Groups of 4. 4 bits. 4 bits, 4 bits. Convert it to 4-bit sections. That's our 4-bit sections. And then using these 4-bit sections, we use our columns method for binary. 1, 2, 4, 8, 1, 2, 4, 8, 1, 2, 4, 8, 1, 2, 4, 8. Do not make the mistake of continuing the columns. These are not powers. We are converting to hex. We are not converting to base 10. If you are converting to base 10, then yes, continue 8, 16, 32, 64 and so on, multiplying by 2 each time. But when you're converting to hex, we only use the 1, 2, 4, 8, nothing else. So these four bits, in other words, this nibble is 8 plus 1, which is a 9. The next nibble is 8 plus 4 plus 2, which is 14. 14 is E. 8. The next one is 2 plus 1, which is 3. 8 plus 2 is 10. 10 is A. So this long binary number is represented by the hex number 9E3A with a small 16 at the bottom to say this is a hex number. Super. So our 16 binary digits have been replaced with 4 hexadecimal digits, and it works the other way around as well. Let's say you had the hex numbers. All you got to do is establish what the hex number is in base 10 and then work out the binary equivalent for that, combine them all up, and there you have your 8-digit hexadecimal number, which has become a 32-bit binary number. A 32-bit binary number. Let's look at decimal to hex. Sometimes you might have to convert a decimal number into hex. Again, we can use the columns process. We looked at this last week. Or you can use the division method. This time dividing by the base number, dividing by 16, saving the remainders and reading from the bottom up the remainders to give us our hex number. So the number 17862, a bit of arithmetic has to be done here. 0 lots of 65536s, 4 lots of 4096s. Again, work out your remainders, continue on, and you should end up with your hex number. You won't get very large numbers in the assessment, folks, so do not panic if you are seeing these large numbers and thinking, how am I going to work these out without a calculator? Okay, you'll have some fairly straightforward numbers to convert. So to convert a hex number to decimal, use the columns method and then multiply each time, then add those numbers up. So here we've got 5 times 4096, F times 256, F is 15, 7 times 16, and B times 1, B is just an 11. Add them all up and we end up with the base 10 number. You can also use an intermediate stage. Take your base 16 symbols, convert them into their equivalent binary nibbles, join them up, place your columns on the top, 1, 2, 4, 8, 16, 32, 64, 1, 2, 8, 2, 5, 6, continue, add those numbers up, and then you could also end up with your base 10 number. Okay, so you could use that method if that works for you and you can easily understand that method, then by all means use that method. Again, similarly, if you have a base 10 number and you're asked to convert this base 10 number into its equivalent hexadecimal number, take the base 10, convert it to binary, and then go from binary to hexadecimal. They all mean the same thing, They're just being expressed in different ways. Sometimes we use the small letter H. So you see the H here? Sometimes we use the small letter H to represent a hexadecimal number or the number 16. Here's one for you to try. Go away, pause the video and try this one. Welcome back. You should have. These are your answers. So remember, computers don't actually store things in hexadecimal. Hexadecimal is there purely for humans. Everything on a computer is stored in binary. If you forget the column headings, it's fairly easy and straightforward to remember those. It's just powers of 2, and you can look at this slide and see how it's how the pattern kind of works its way out. Similarly, base 16 columns line up with base 2 columns. Here's some more for you to try. Go away and try them. Pause the video. Welcome back. This is what you should have had. Okay, again you can try this one as well, just see exactly how this is worked out. So remember the 4 nibbles: 1, 2, 4, 8, 4 plus 1, 5, this one is 0, 1, 1, 0, 1, 1, 2, 4, 8, and so on. So try a few of these until you get the process and understand the process. Just to summarize then, computers manipulate values in binary. They store numbers using 1s and 0s, but for humans we display them in hexadecimal. Each group of 4 bits represents 1 hexadecimal digit. Hex digits go from 0 to 9, then A to F. Value of each hex digit increases by a power of 16 as the columns move from the right hand side to the left hand side. Hex values are represented by either a subscript 16 or a lowercase h. That's us, folks. Thank you.